So what I thought I'd do, because I didn't know exactly what I was supposed to do, is I wanted to sort of communicate how exciting it was to be using Keck when it first came online, and how, and that kind of the feeling of, it was almost like a frenzy of things that one could do that could never be done before. And it's going to be sort of a personal experience in order, because that's all I can tell you about. I don't know how other people felt, but I suspect similarly. And Keck has been, I feel like it, I mean, I first became aware of Keck, as I'll tell you in the next slide, when I was a first-year graduate student, showed up at Caltech, terrified of everything. And I was terrified of my thesis advisor at first. Right at the same time I arrived, I seemed to be lucky to arrive on the scene just as the Keck project started in 1984. And I heard Wall grumble about his duties on the Keck Science Steering Committee, which was the original version of the body that some of us have spent decades on since then. You know, it's kind of really strange to think about the fact that at that time, as the Keck project, as people were waiting for Keck, all of a sudden it was going to be real, to realize that it was still the 200-inch Palomar was the largest telescope, and that had been built like 50 years earlier. So it was just a really odd time, and I'm going to try to tell you about what the whole picture of cosmology and galaxy formation was then. It was really the Wild West, I'll tell you, in the late 80s and early 90s. Anything could have been true, and we couldn't have said that it wasn't. And I'll talk more about that in a minute. So after 5 years, I went up here, spent 4 years in Campbell Hall, the old one. Haven't seen the new one yet. It was a great time, and I heard it was so exciting because High Spinrad was there, and High was the most excited. He was like a little boy excited about Keck, and he would constantly be harassing anybody who knew about anything. When was the first camera going to be available, because he had something that he wanted them to do. And James Graham was the closest, I think, in the department at the time to what was going on, because he was involved in NERC. He was on the original NERC team. And of course, James wasn't quite the same personality-wise, and so he would, you know, and little did anyone know that James would never get a clear night on Keck in his entire career. That was a joke, but almost true. Anyway, then right about the time that things were getting exciting, I had to leave because I had to get another job. And so I moved to Boston and thought, okay, now I'm stuck with two 2.4 meter telescopes. There's the one at MDM that MIT then was a part of. And then there's Hubble Space Telescope, which right around that time was finally about to work. It was 1994. Remember, it was one of the most embarrassing episodes in astronomy history when Hubble was launched, and it had spherical aberration, and we had to wait for 3 years for it to be fixed. And it was just getting fixed in 1994, so that was kind of exciting. But I was really frustrated because I would get emails from Wall, who was not very nice about it. He would say, look at these amazing spectra from high-res. And he would just, you know, this is, you know, they were amazing. High-res was really exciting to me because I grew up doing quasar absorption lines for my PhD thesis. And so this was like, oh, I might as well just quit. So they were taunts, I thought. And then I got a chance to go back to Caltech. I thought about it for maybe 3 seconds before I said yes. But then I couldn't go for another 18 months after that for various reasons. And so my very first trip to Keck was in 1995. And it was to visit Wall because he had a 3-night run. And of course, it was August, and the fog was sitting on top of the mountain and never left. But I did get to spend 3 nights wandering the halls up at the summit and actually got a chance to see everything. It was unbelievable. So anyway, I show up in Pasadena. I had to rush to Palomar because we had an observing run with the prime focus camera because we were getting ready for the very first night on Keck. That was October 1st, 1995. And that, and I'll tell you more about that, because it's kind of like a ridiculously exciting very first time, because we've been working on something trying to, it was kind of one of those high risk, possibly high reward kind of projects. And, you know, didn't really expect that it was going to work, but we were getting ready to try. Talk more about that in just a second. And let me just say that I owe so much to the Keck Observatory. I mean, it's embarrassing. I added up all the observing time over the last 28 years. It's 510 nights. So, yeah, so I've spent a significant fraction of my adult life observing at Keck, literally. And hopefully some of it was useful, but it wasn't all clear, so maybe that. But I have to say that a lot of my approach to Keck in the time since the first few years is knowing that I have to pay back big time. I mean, not just, this is, how much is that worth? It's worth a lot of money, but you know, and how do you pay back? Well, you work on the science steering committee and you build instruments for Keck that everybody can use. That's all I can think of. All right, so what was the universe like in the early 1990s? As I say, it was almost anything goes. If you go to a conference, and the conferences then were very wide-ranging, like you'd have cosmologists and people interested in galaxy formation at the same conferences, which doesn't happen so much anymore. And the reason was nobody knew anything. We didn't know what, you talk about the Hubble disconnect. Hubble constant was either 50 or 100, and nowhere in between, literally. There were two, it was bimodal. And theory, all theorists accepted cold dark matter as the paradigm, but no one was talking about low density cold dark matter. When they were talking about cold dark matter, they meant CDM with omega matter equal 1. And everybody who ever observed anything knew that that couldn't be true because it wasn't consistent with really anything. But it was just at the, let's face it, we didn't know anything. People were looking for primeval galaxies like Jim Peebles predicted, 20 years earlier, giant bursts of star formation forming a whole galaxy at one time, using Lyman alpha, for example, and nobody was finding anything. And then people were obsessed with what they were calling faint blue galaxies. And this came from the first very deep CCD images of the sky showed that there were lots of galaxies, and they were faint and kind of blue. And there was, it's not really exaggerating things at all, that people would use galaxy counts to try to see what kind of universe we lived in, just because the volume element was different in the different cosmologies. And every time you wrote a paper, you had to do it for 3 different cosmologies because it could make a big difference. And it was a pain. It really was. We really needed at least to get Hubble constant to, 10% or so. Thankfully, that happened soon after. But really, the problem was that you could count lots of faint galaxies. You could take deep images of the sky. Some of the pioneering work of the time was done by the group at the University of Hawaii, Simon Lilly and Len Cowie. But it was really, it was very limited what we could say. And the problem was we couldn't get spectra of the faint things. Everyone wanted to know what they were and where they were without the ability to do anything about it. So at the same kind of conferences, you would have a disconnect between the people working on galaxy surveys and the people like me who were working on quasar absorption lines. So you get the galaxy formation, people would be talking about their deep surveys with a median redshift of 0.3 or 0.4. They go down to B of 24 or something like that. And it turned out that when you go fainter, the median redshift doesn't really go up because you just get more and more fainter galaxies that are nearby. And so there's all sorts of speculation. Maybe high redshift galaxies don't exist. Maybe there's nothing there. Maybe they're all in little tiny pieces, just like omega matter equal 1 CDM predicts. Meanwhile, those of us working on quasar absorption lines were finding metal containing absorption line systems up to at least a redshift of 3.5 or 4 at that same time. So we were pretty sure the galaxies did exist and wanted to find them so that we could point to them and say, galaxy people, looky here, we got high redshift galaxies. So we're trying to think of things don't have strong Lyman alpha emission like they were predicted to, maybe because they didn't form all at once. Maybe Lyman alpha just doesn't get out of the galaxies. So we were just thinking of alternatives and some way of making a plausibility argument that, looky here, here's a high redshift galaxy. So the way we approached it was to take deep images of the sky along where the quasar that we knew had a metal-containing Lyman limit system at high redshift greater than 3, and we designed a filter system so that it would be sensitive to the Lyman limit, where everything we knew about the universe says that it would just disappear in the bluest passband, and redshift 3 was simply the lowest redshift where you could do that. So we spent 2 or 3 years making these plausibility arguments based on that kind of thing, including, finding plausible candidates and making predictions about where we should look in 2-color space to find these things. And we were using pretty mediocre facilities to do the imaging. And it was mostly because this was the era when people were starting to convert to these big prime focus imagers, and almost all of them used correctors that didn't transmit in the ultraviolet. And so we had to use Cassegrain CCDs with tiny little fields of view to get the U-band sensitivity. Anyway, so we would do the deep imaging. We would find a handful of things up here in a small field of view, and some of them were right near the line of sight to the quasar. So we thought, this could be real. These could be associated with these absorption systems, and maybe we can prove that this is a way to find these things. So, maybe not. People don't believe things that are not very plausible like this. And meanwhile, Keck was doing really great stuff already. This is before I ever touched it. Including a lot of great stuff with high res, as I mentioned. Everything from the metallicity of intergalactic clouds to just the kinematics of damped Lyman alpha systems seen with beautiful high res spectra kinematics. The Lyman alpha 4 is a redshift 4. Deuterium abundance, as John mentioned earlier. Great stuff. Meanwhile, with low res, another of the early light instruments. NERC, of course, was the other early instrument. Low-res had a bit of a teething issue that lasted a bit longer. But there was great stuff being done. But it was mostly based on counts of faint galaxies. That was all the rage back then. And it was doing it better than anything had done so far. And high was observing things he knew about already, and he was going to get a better spectrum with Keck. That's low-hanging fruit that was perfectly reasonable. Here's the spectrum of then the highest redshift galaxy known, a radio galaxy, which is what the highest thing was. And here's the first faint galaxy redshift survey conducted with low res. And yet again, even though it was selected in K-band instead of B, they were still finding a pretty low redshift. And when you go fainter, you don't seem to be going more distant. So what was that? What did that mean? So these young guys show up on their very first night getting to the telescope, and we just finished imaging these fields at Palomar, so we had our slit masks all ready, and we were so damn lucky. This is Kurt, who was my first graduate student, who has since left astronomy because after a decade of being one of the most productive young astronomers in the world, he decided the next decade wasn't going to be as fun as the previous one, and so he went off to do something else. I'm sure he's having a good time, whatever he's doing. Anyway, on the very first night, we got 20 redshift greater than 3 galaxies confirmed spectroscopically. Now, when people would ask, well, is it the most distant galaxy? No. It's not, High's galaxy, redshift 4.35 is higher. But the point was, and it's not very exciting to say it, but now we know how to find galaxies at pretty much any redshift. We just have to have the right filters to do it. And that opened up all sorts of possibilities. And I just wanted to mention, this is also a weird thing. Our very first spectrum, which is one that we didn't do with a slit mask, it was done with a long slit, was at minus 38 degrees because all of our imaging time had been at Southern Hemisphere telescopes. Amazingly enough, we got the first Lyman break galaxy spectrum at minus 38 degrees. Just a trivia. Now, what do you do now? So we know how to find things, and pretty much we don't know anything about these galaxies. We don't know their masses, stellar masses. We don't know their dynamical masses. And there are all sorts of things that you could do if you had the right instrument to do it with. But the thing that occurred to us as being the lowest hanging fruit is let's get lots of them in similar regions and find out how they cluster. Because the theorists at the time were telling us this is a great test of CDM, because if you can measure the abundance of something and the strength of the clustering, you can set a mass scale for the dark matter halos. And this is what we tried to do next. So we were rushing around like crazy, doing 4-meter class telescopes for imaging and then going to Keck and getting spectra. And we got several hundred of these in the next 18 months or so. And it became possible to measure the, the clustering properties. And I'll tell you about that in just a second. We were also banging our heads against the wall to get near-infrared photometry, which was needed to get an estimate of the stellar masses. And this was the first of Alice Shapley's thesis projects, was to collect all these NERC images that were all these little 38 arc-second patches. It was we could go very deep, but we would only get one or two at a time, so it was, well, tedious isn't the word. It was exciting, but time-consuming. So we go back the next season with our same field that we started with, and that's not supposed to be there yet. Let me see if I can fix that. No, I messed it up. Anyway, this comes later. But so we went back to Keck the next year. I guess that was 96. And low res had moved from Keck 1 to Keck 2 at that time. Keck 2 came online right around the beginning of October of 1996. We had a run in the first week. And we noticed, as we were measuring redshifts from slit masks coming off the telescope, man, a lot of these have the same redshift. Isn't that weird? So literally, We should have gone to Las Vegas. I mean, the very first field where we got any substantial number turns out to be one of the largest overdensities known to this day at high redshift. This is the famous SSA-22 protocluster at redshift 3.1. And it was the first hint that these things were really strongly clustered, and we got the ability to say something about what that might mean. We did a bunch of other fields similarly, and after a few hundred, we could actually, and this is a lot of, Kurt was a closet theorist, and so he knew how to do all the right calculations to figure out how that mapped. Nowadays, people call this method abundance matching, where you match the abundance of something and the clustering properties, and you get a dark matter halo scale out. But it turns out that we could say that these things were very consistent with the CDM paradigm, more consistent with a low-density CDM. And they were living, these faint galaxies are living in Milky Way-sized dark matter halos, so they're pretty big galaxies for their era. And that was exciting, and then Hubble Deep Field happened, and you could do this kind of thing with Hubble. And that was done. The famous Madal plot was first, came out of this Hubble Deep Field a couple months after it was released to the public. And so Hubble started to play in this game, but it was really quite a while before Hubble had a big enough field and enough filters. It was really with C3 when it came along later on to do a lot of this. So we were trying to say, well, let's see what happens if we try to go to higher redshift. Here's redshift 4. We figured out what range of reddening and everything we'd already seen in the redshift 3 population, predicted where they would be if they were out at beyond redshift 4, got a bunch of photometric data, candidate lists, and got some spectra. So it turns out it could be done. However, low res wasn't really the right instrument for it. It's really a struggle because low res used an old Tektronix detector and it fringed like crazy, and low res flexes all over the place. It was very difficult going, but we got 50 or so, and then we said, this is too damn hard. Let's go back and do a proper job at lower redshift, because that's where we want to be anyway, because that's where we get all the information about the nebular emission lines falling in the right place with respect to the atmospheric bands for near-infrared stuff. And we made luminosity functions and early versions of the Madal plot, so to speak. This is really the state of what we knew at the time that James Webb became a real thing in the late 1990s. It was just the hope that there would be plenty of stuff out here, since we knew that there was stuff now in there. Okay, so near-infrared spectroscopy, that was really super hard at the time because we were too early for NIRSpec, although we really beat our head against the wall by going to UCURT, using whole night integrations and fingers crossed, and we detected 5. They're not very impressive, but it was doable, and we were learning the first things about these things. And finally, NIRSpec arrived, and NIRSpec wasn't really designed for faint targets like this. This was the mode, the low-resolution mode, that was really just the cross disperser being used as the primary disperser. But we could do 2 or 3 every couple of hours, and we got small samples. And we just banged along doing that. But to do that, we needed to find the redshift 2 to 2.5 things. And fortunately, how did that happen? It got turned. Fortunately, right about that time was when I was feeling really a lot of guilt about getting too much stuff for free. And so I volunteered to do the blue side of low res, the upgrade. And I just want to show things that we should never do again, okay? Everybody listening? So there were a lot of things that had to be added to an existing instrument that was already shoehorned into a small space. And to do that, we somehow agreed that we would do the whole thing in 6 weeks and have the instrument back on the telescope and ready to observe. And so we brought it down to headquarters in Waimea, and it was actually out in the parking lot for a lot of the time because we had to cut big holes in the various bulkheads and all that kind of thing. And you might recognize some of the people here. This is the crew primarily from Caltech. This is John White, who used to work at Keck, and I think he went to work at Gemini after that. That was June of 2000, and it was wrapped in plastic and brought down in a truck. Those guys were there for 6 weeks, fighting with each other and working out among the plants in the parking lot. It all got put back together, went back up to the summit, and allowed us to test out how to find lower redshift galaxies. And this is before big near-infrared imagers, so we wanted to do the whole thing with just optical photometry. So we figured out where to look and made some little swaths in color space, and then went and showed that we could do this so-called redshift desert between 1.5 and 2.5. That was a thing back then, too, because near-infrared spectroscopy hadn't really come of age yet. Got it? Yeah, I'm over time. I'll go fast. So I wanted to mention, though, that it was surprising, but this is right around the late 1990s was when all the submillimeter explosion was happening because SCUBA had come online, and the thing's called SCUBA galaxies because they were detected only at 850 microns with the new SCUBA instrument on the JCMT. But almost all the spectroscopic redshifts for these things were obtained with a UV-optimized spectrograph. It was all done with the blue side of low res by this group, and they spent a lot of time doing that. And this was an important contribution early on when we were trying to understand the demographics of things that are really dusty, things that aren't as dusty. It was all like a big mess. Finally, we put together a sample of 100 or so observations with NIRSpec of H alpha in the redshift 2 sample that we just found. And this was most of Don Erb's PhD thesis. And we found that there is a mass metallicity relation among the redshift 2 population. You can see compared to the SDSS sample, things are pretty different. There was a hint that something weird's going on in the BPT diagram. We could get to that later. Meanwhile, all sorts of other things were happening. It was really unbelievably, you blink and we're in a new paradigm around that time. This is around the time that the VLT, Subaru, and Gemini were coming online, so there was competition now, especially from initially the VLT. And this is about the time that people started looking for things that were already dead at high redshift, which are much harder to identify and to confirm because they're really faint at any of the wavelengths we could observe them. And as Alex was talking about this morning, this is about the time when all the things coalesced to tell us that what kind of universe we were living in. We didn't have to worry about H naught anymore. We could just put little 0.7 for the little h, and everything we calculate could only be done once instead of 3 times. ESI came online in 1999. DEMOS was a little bit later, mostly because the SSC, we had to decide which of those should come first, given odds of which would take longer, because we needed a dark time instrument desperately for the second telescope. And ESI got chosen because it looked like it was closer, because they were both being built at Lick Observatory at the shops in Santa Cruz. And then OSIRIS came online and for the first time allowed us to do AO-assisted things. And I just wanted to say, we started thinking very early on about how to get multi-object spectroscopy in the near infrared. And there was a 2-year study that then failed at its PDR. And I think it might be the only instrument that we've ever entertained that failed at that point. And it failed because it was just too ambitious. It was too much, too expensive. And so there was a committee, there was a committee chaired by Tom Green, who you'll hear from tomorrow, Tom, who chaired this little committee where we said, what does this thing have to be able to do at the very least? And it was very successful, and it started a month after Kermos failed. And then only a couple months after that, we started the Mossfire project, which then took 8 years to finish. There it is, 8 years later. It's basically low res in a cryostat, and it was very challenging. Even Keith Matthews, the world's expert in these kinds of things, I think would admit that it was challenging. And there it is in a big box about to leave, and this was so fun. It was a really 50-50 collaboration between Caltech and UCLA. It was really the first time, I think, that there was a total collaboration between different institutions, and it worked great. We all got along the whole time, and it worked. And that is the most amazing feeling. I think it's more amazing for me than some of these scientific things when something you work on for 8 years actually works. And you think about how many people had to do things right for that to happen. It's just unbelievable. That's the commissioning, and these are some of my favorite people who are all graduate students formerly at Caltech, except for Max, and Max is the sort of shadow advisor to every student I've ever worked with, because he's pretty much the nicest guy on earth, and he's a great mentor, and he's been along the way for everything. And Barbara, who many of you know, I'm sure, used to make a habit of taking pictures of everyone that when they visited Keck for the first time. And so all these pictures, except for Allison and Yugong, who unfortunately went out there after Barbara stopped doing that because she retired. She's not allowed. But these are all pictures taken on first trips to Keck, which I think is a great, I think we should somehow get back to doing that, because I still have my 30-year-old, 28-year-old picture on my Observer login page because I'm too lazy to change it, but also because it reminds me of being, having my whole life and career ahead of me and just being really happy. Sometimes that's necessary to see. Here's a bunch of the crew when we got together at some conference or another. And I just wanted to say that Keck has played a major role in just about everything at high redshift. Hubble will claim a lot of credit for all of this, but really it was the Keck spectroscopy that nailed it. And Hubble basically came and did the much higher redshift stuff, along with Deimos later on. But Keck was really what opened it up in the first place. I just wanted to admit that I'm torn between whether it's more fun to find a bunch of high redshift galaxies for the first time, or work on an instrument for 8 years and see that it works, which is more amazing, I think, when you think about it. And I just wanted to acknowledge that all of this is due to Jerry and lots of other talented people, but Jerry was great, and serving on the SSC for many years with him, he would always ask the simplest questions and would take the longest time to argue about them, but they always boiled down to, it's just freshman physics, he would say. And we'd all say, okay. And he never thought something was impossible if it didn't violate the laws of physics, and he had that attitude his entire career, as far as I can tell. and that is unusual, and you know, it was really important to the success of this project. Thank you.